We've already used a transformation matrix to transform one point. What I want to do in this video is transform a series of points. And so I have these position vectors P1, P2, and P3, and I've plotted them right over here. And you could imagine them to even be vertices of a triangle that looks something like this. That's one side, that's another side, and that's another side, right like that. And what I'm curious about is what happens if I would transform these 3 points? And like the last video, I could apply this transformation matrix separately to each of them to see what they transform into. Or instead, I could take this transformation matrix, and multiply it times a matrix composed of these position vectors. So let me do that. So let me take my transformation matrix. So let me copy and paste that. So copy and paste. So I'm going to take my transformation matrix, and I am going to multiply that by a matrix that has all 3 of these position vectors in it, where each of the columns of this matrix is going to be one of these position vectors. So the first one is 2, 1. Then we have -2, 0. And then we have 0, 2. 0, 2. So one way you could think about it is we're taking our transformation matrix and we're multiplying it by a matrix that is composed of the first column is position vector 1, the second column is position vector 2, and the third column is position vector 3. Now, what is this going to give us? Well, this is a 2 by 2 matrix. We're multiplying it by a 2 by 3 matrix. So matrix multiplication is defined over here because the number of columns here is the same as the number of rows here. And it's going to result in a 2 by 3 matrix. So it's going to result in a 2 by 3 matrix. So 2 rows and 3 columns, which we could imagine represents 3 new column or 3 new position vectors. So what's this going to be? So let's go step by step. So this first entry, first row, first column is this row times this column. So 2 times 2, which is 4, plus 1 plus 1. So it's 4 plus 1. So this is going to be 5. Let me do it in the same colors. So this is going to be 5. -1 times 2 is -2. That's -1 times 2 is -2. Plus 2 times 1 plus 2. That's -2 plus 2, which is 0. So we already see it transformed 2, 1 to 5, 0. 1, 2, 3, 4, 5. So if we consider this P1, we consider this P1 prime, P1 after our transformation. Now let's go to P2. 2 times -2 is -4 plus 1 times 0. So it's -4 plus 0, which is just -4. And then -1 times 2 is +2 plus 2 times 0, which is just going to be 0. So it's going to be +2 plus 0, which is just 2. So -4, 2. -4, -1, 2, 3, 4, 2 is right over here. So if this is P2, this was P2 right over here. This is P2 prime. This is P2. This is position vector P2 prime, or the position that position vector P2 prime would specify. And then finally, let's look at P3. So we have 2 times 0, which is 0, plus 1 times 2. So it's going to be 0 plus 2, or just 2. And then we have -1 times 0, which is 0, plus 2 times 2 is 4. So we get the point 2, 4. So 2, 1, 2, 3, 4. We go right over here. So if this is P3 right over here, this is P3 prime. And so something interesting has happened. We now have the vertices, you could imagine, of another triangle, of a new triangle. of a new triangle that looks something like this. That looks something like this. That looks something like this. And so what you could imagine is, actually let me draw it a little bit. Let me draw our new one with this blue color here so we can see it a little bit better. So we went from that smaller triangle. We went from that smaller triangle to the larger one. This is the smaller one right over here. That's our smaller triangle. To the larger one. Or another way you could think of it, this entire triangle was transformed. And right now we only transformed the vertices, but it actually turns out, and I'm not proving in this video, that if you took any of these points on this triangle, it would have transformed to a corresponding point on this larger triangle. And what's neat about this is hopefully you're starting to appreciate the power of a transformation matrix. And hopefully you're starting to appreciate why this is useful as you start to think about things like computer games and animation. Because what transformation matrices allow us to do, and this is what these computer programs that allow us to do, view things from different perspectives, what they're actually doing under the covers is they're using transformation matrices and they're multiplying them times coordinates in order to get new coordinates based on the position or the perspective of the player or the position or the perspective of the camera or the virtual camera in a kind of a computer graphics world. So several neat things here is we haven't just transformed a point now. We've transformed 3 points, which could represent the vertices of a triangle. And you see this kind of expansion and rotation that seems to have happened when we used this transformation matrix. If we use a different transformation matrix, we would have a different transformation. And not only did we do it, but we saw that we could do it with multiple position vectors at the same time. I could have done it independently and gotten the same result, but this is hopefully starting to show you the power of matrices and why it also could be useful in things like computer graphics and animation and things like that.